Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Asymptote River College in Sacramento, California, and this is going to be somewhat of a short video. We're right in the depths of graphing using transformations for functions, and if you're doing this in the order with which I recommend, then you have just reviewed how to graph functions using vertical and horizontal shifts, or what we call vertical and horizontal transformations. Now we're going to talk about the reflections, and again, this is something that is often or should be a review for you. My disclaimer is that if there's any professor watching this, they know, I know, you know, that this is not how you would normally teach it. This is how you would review these topics, because again, you have seen these. So let's go ahead and talk about these. Actually, I will adjust that statement. There's probably one reflection here you might not have seen. There could be. Okay, so let's talk about these. Vertical reflection. This is the one I think most people will see initially in an Algebra 2 course. Given a function, a new function, g, which is just the opposite of that original function, is a vertical reflection of the function f, sometimes called a reflection about or over the x-axis. So it reflects over or about the x-axis. I would rather give you an example of this before I go into the second version. So let's go ahead and say, I'm just going to pick on the square root function because I like the square root function. Somebody hands you that function, you should immediately know it looks like this. There should be no doubt in your mind. And you do know it goes through 0, 0, and it goes through 1, 1. Most base graphs go through 0, 0, and 1, 1. If you don't recall, we talked about the base graphs briefly last time, and then I also talked about them in a previous lecture, but I will hop back and just showcase from last lecture. These are the base graphs. All of them, with the exception of this guy, and this guy, all of them go through the points 0, 0, and 1, 1. The three I've highlighted, well, two of them go through 1, 1. Let me underline them. That goes through 1, 1, and so does that. This guy right here is kind of the oddball of the group. It's just a horizontal line, so there's not much. Actually, I really dislike that being called a base graph, so I'm just going to get rid of it. So I'm reducing our base graphs to 8, just because I think that other one's silly. It's included in the OpenStax algebra and trigonometry course as one of the base functions, but really nobody else does that. So going back to this square root function here, if we want to graph y equals the opposite of the square root of x, what it's going to do to that graph is reflect it about the x-axis. It's called a vertical reflection. And so our reflected curve will look like this. It looks like the same curve, it's just been spun around the x-axis. It still goes through 0, 0, but it does not go through 1, 1 anymore. It goes through 1, negative 1, because all the y values are the opposite of what they used to be. That's what that negative does, is it makes all the y values opposite of what they used to be. So that's a good example of the vertical reflection. Once somebody sees it once or twice, they're pretty solid on that. The one you might not, and this is a big question mark, I'm not sure if your college covers this. Our college waits until our trig course to talk about this, I think. I'm almost positive. So let's talk about it here. The horizontal reflection of a function. So given a function f of x, a new function g of x, which is f of opposite of x, is a horizontal reflection of the function, sometimes called a reflection, about the y-axis. I'm going to highlight that. So it basically takes all the x values. Maybe I should highlight this. So the top one there in red, g of x equals negative f of x, it takes the y values and returns their opposites. So it just basically throws negatives in front of the y values, as we see right here. However, g of x equals f of negative x, this guy right here, takes all the x values and returns their opposites. So that will actually reflect about the y-axis. And so a simple example, again, stealing the square root, y is equal to the square root of negative x. Now, some people will say, you can't have a negative underneath the square root. And I would say, you're absolutely right. On the Cartesian coordinate system, because the Cartesian coordinate system only deals with real numbers, you're absolutely correct. The square root will not take a negative as its argument. And that's why this square root will not take a negative as its argument. If you think about what the negative x does, as far as the theorem that we've just cited, it takes that square root function and reflects it about the y-axis. And so you get something that looks like this. Remember, it originally looked like that in black, but now it looks like this. All the x values are their opposites. The opposite of 0 is still 0, and the opposite of 1 is now -1. The y value is still 1 though. And to respond to the statement, I thought you couldn't have negative numbers as an argument inside the square root, these x values totally are negative. I absolutely agree with you. But guess what you're doing with those negative numbers? You're taking their opposite. So you're actually, as far as the radical thinks, and it doesn't because it's just a mathematical operator, but whatever. As far as the radical thinks, you're plugging in positive numbers. So it's perfectly legal and fine. All right, let's move on to actually our real first example. Just fast forwarding here. So let's graph that function. Again, very, very nice function. You should know the absolute value base graph. Everybody calls it the V function. Just kind of quickly jotting this down by hand. Remember, it goes through 0, 0 and 1, 1, as all of our base graphs do, except for 1 over x and 1 over x squared. And what you want to do is graph the opposite of the absolute value of x, which means it's going to take all those y values and it's going to flip them about the x-axis. The resulting curve, and it is a curve even though it's actually looks like two lines, it's technically called a curve still, goes through 0, 0 and 1, -1. Yes, there are an infinite amount of other points on this curve, but for our purposes, plotting 2 is perfectly fine. And remember what I said last video, you should not actually use point plotting to graph curves like this. If they're base functions, you should just immediately know what they look like. And if you say, but I don't, that just means, guess what your task is? To learn them. That's it. That's all you need to do. There's only 8 of them. And most of them are very familiar to you. All right, so that's it for this first example. Let's try another one. Ooh, this is a good one. I like this one a lot. All right, graph this function. Now, first thing you should do is identify what the base graph is. So the base graph or the base function is what occurs when you basically pull away that +4, that +3, and the negative. The base function is a 1 over x. That's, of all our base graphs, that's the one this is going to look like. And so I'll go ahead and just chicken scratch that out. And I said it a moment ago, but 1 over x and 1 over x squared are the two base graphs that do not go through 0, 0. In fact, they both have vertical asymptotes at 0 and horizontal asymptotes. I like horizontal asymptotes to be drawn in green for some weird reason, but they have horizontal asymptotes at y equals 0. If you don't recall, horizontal asymptotes are just the tendency for the curve as it goes to the edges of your graph, as it goes this way or that way. Sorry, that arrow was supposed to go that way, but it just did not work out for me. Beep, beep, beep. There we go. As you go to the edges of the graph, notice the black curve there starts to hug the x-axis, which is also known as y equals 0. So that's why we call that the horizontal asymptote. The vertical asymptote, on the other hand, is kind of the x value that causes a singularity. It causes this division by 0. And in fact, if you've ever played with magnets when you were a kid, which I used to, I played with magnets when I was a kid, you would have a magnet, let's say it's positive polarity there, and you have a magnet, let's say it's negative polarity there. They would actually glue together, right? They'd snap right together. But the moment that you switch sides and that became positive polarity and you tried to push them together, they would sort of like, as you try to push them together, they would try to push away. One would end up slipping upward, the other one would slip downward. That's because you have a singularity occurring when you're trying to push those two polarities together. So if they're the same polarity, they will not attract, only opposites attract. And so when you try to push those together, they'll push away from each other. They might push in the same direction, by the way. They might both push up, but they still showcase a vertical asymptote. And that's exactly what we have there, vertical asymptote. I'm going to get rid of my drawing because I'm not an artist by any stretch of the imagination. And go back to this example that we're talking about here. So let's see, we drew the base graph. Oh, and I did say it does go through 1, 1, so I'm just going to plot that. And if your instructor requires 2 points to be plotted, well then fine. It goes also through -1, -1. It's symmetric. Now, how am I going to rebuild that g of x? Well, there's a trick here, and it's a very important trick to pay attention to. So how does it work? Well, you sort of pre-work the function g of x here. I would take this denominator and factor, incredibly important, factor a negative off of the x and the 3. Very, very, very important. The reason why is that negative, it does a reflection, and we're going to see it in a moment, and the 3 will do a shift. So, and to get the proper shift, you have to have the coefficient of that x to be 1. And we'll talk about that in the next video. But for right now, I'm just going to hand wave it a little bit. And I'm going to say that this is the same thing as -1 over x minus 3 and then plus 4. Now, at this point, I might have some very astute students who look at this and say, wait a second, could I have just left that negative in the denominator? And the answer to that is yes. But if you can simply factor that negative out to the front of the function, I would recommend it. It's just a little cleaner that way. So I have moved this negative to the front of the function for several reasons I don't want to go into, but there you have it. And so that negative in front, now that I've written it that way, will reflect this function. So I'm going to graph y equals negative and then 1 over x. Notice I'm reading it from left to right. So I'm applying the negative first. And you don't have to spend a lot of time on this. I'm just talking while I do this. So obviously it takes me a little more time talking and doing this at the same time. But really, you can kind of chicken scratch this out very quickly. Nobody expects, well, I can't say that. Maybe your instructor does expect perfection on these sub panels that you're drawing here, but I certainly would not. I would expect to see kind of what moves are being made here, but I don't need to see a ton of extra complexity or precision here. So again, this is still x equals 0. This is still y equals 0. The values slightly have changed, right? So instead of 1, 1, this is 1, -1. Instead of -1, comma, -1, it's -1, comma, +1. The y values got multiplied by a -1. Now, again, reading from left to right. We've already taken care of that guy. Now we'll go ahead and take care of this one. X minus 3. Okay, so the argument of my function. Remember, the function is basically 1 over x. But instead of 1 over x, we have 1 over x minus 3. So the argument is x minus 3. The only way to turn that into 0 is to let x equal positive 3, which means that that shifts our graph here 3 units in the positive direction. Again, the only way to turn that denominator into 0 is using x equals 3, which means that's how far it's been shifted and in that direction, positive 3 units in the x direction. Now, to be honest with you, if I did this and I know I have vertical asymptotes, here's how I would do it. Notice I'm just copying the graph, right? But that's because it's just grabbing this graph here and moving it over 1, 2, 3 units. The y-axis is staying put. The red lines are not. So the y-axis is still right here. I've just moved the red crosshairs, if you will, 3 units over to the right. That's all. There is an x-axis. The x-axis is hidden underneath this horizontal asymptote, but this is y equals 0. This is now not x equals 0. This is x equals 3. It's been shifted 3 units to the right. And our points, well, they were 1, negative 1. This was 1, negative 1, but you're adding 3 to its x value, so it's 4, negative 1. And this guy over here, that was at negative 1, positive 1. Again, you're adding 3 to its x values, so it's 2, positive 1. And we're almost done, because now we've taken care of the flip right there and the shift right here. Now that last piece just moves those crosshairs up 4 units. So I'm going to grab these crosshairs here and move them up 4 units. So instead of being at y equals 0, they'll be at a height of 4. Since this will be our final graph, I'll be somewhat careful with this. I'm going to be somewhat precise. So again, I said it earlier, but I'm going to slowly do it now. I like red for my vertical asymptotes. So I'm just going to go ahead and dash out some vertical asymptotes here. They occur at x equals 3, or it occurs at x equals 3. The horizontal asymptote, I said earlier, I like to use green, so that's what I'm going to use here. And that horizontal guideline, or asymptote, I like to call it a guideline, but whatever. That's not going to be at y equals 0 because it's been lifted up 4 units. So I'm going to call this y equals 4. Now from that, I could easily tell you where the y-axis is. So I'm going to just say, if that's x equals 3, then maybe this is 2, 1. Okay, so here's the y-axis. And if that's y equals 4, this is probably 3, 2, and then 1. And so this must be the x-axis. Notice how it's starting to really take shape. I'm almost done. I'm just going to copy the curve now. The curve looked like this. It's not totally exact, but wonderfully close to it. Oops. Almost ran into my horizontal asymptote. That actually reminds me. That's not the purview of this video, but it is the case that a curve can actually hit its horizontal asymptote. It cannot strike its vertical asymptote. Yeah, that's all I'm going to say. That's something that can be treated later on in a pre-calculus course. I actually kind of do it in a trig course, so college algebra and trig, you'll hit it in here too. But we're not done. We still have these points right here that we're at. Let's see, this one was at 4, what was it? 4, negative 1. Well, now the x value with this last shift did not change because we just moved things up 4 units. So if you add 4 to this y value here, you'll get 3. And so, which by the way tells me, since I labeled this as a height of 3, I should probably plot it right there. So I'll just do that, 4, 3. Which means my scale is slightly off. Not a huge deal. I plotted it. That's all I care about. And then the other one was at 2, 1. Again, the x value didn't change. Here, I'm going to slightly make it if you miss your mark, make a bigger point. And so this is 2, add 4 units to 1. So 2, 5. And 3. And there you go. That is a semi-decent graph. I used to be a major stickler about this. I sort of still am. I want you to notice there is a slight flaw with my graph other than the scale. Slight flaw is that it's technically not a function. You can see it's sort of bending back upon itself there. That's a big no-no. You don't want that to happen. So I try my best to make it a function by not having it bend back upon itself. That's more of me being a stickler for myself, just because I dislike saying something is a function if it doesn't look like a function. That's kind of a big no-no. Anyhow, so that's a review, very fast, right? Fast review of horizontal and vertical reflections. Now, before I step away from this, notice that I didn't really have something that had a vertical, a reflection about the y-axis, or so you may think. But if I actually go to the original function, 1 over x, and I say, okay, but I'm not graphing 1 over x, I'm graphing 1 over negative x plus 3. Well, that negative on that x, technically, by what our theorem said, should reflect about the y-axis. So it should take this curve and reflect it about the y-axis. But isn't that exactly what it would look like if it reflected about the y-axis? So in this case, a reflection about the y or the x is exactly the same, but you could have done it that way. However, no matter what, to figure out what the horizontal shift is, you would still have to factor the negative. Oops, that was supposed to be a highlighter and it wasn't. So you'll still have to factor the negative off of these two terms in the denominator. That's to find the actual reflection, or the actual shift. And that is going to be sort of a topic. That's going to be a topic, but not in the next video. The next video, we're going to focus on even and odd functions first, for a very specific reason, because they help us graph. And then we'll worry about, well, what if that wasn't a negative on there, but instead of 5x or something like that.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.